Let's see first order versus second order elements. So we will continue with previous chapter example, that is plate with hole. We have taken a tour of PrePoMax user interface and FEA workflow with a simple example, and we meshed this component with first order TET elements. Okay, so let's go a little deeper. Now, the objective of this workshop is to understand the element in stress concentration zones, that is first order versus second order elements. So to compare our FEA results, we will use the analytical peak stress. Okay, so this is the formula for analytical peak stress, which is given by sigma max equal to KT, stress concentration factor, multiplied with nominal stress sigma norm. So peak stress near hole is given by sigma max. Okay, and sigma norm is the effective stress in this cross section near hole, okay, which is given by force by area, and stress concentration factor is given by this formula. So by substituting all the values d, t, w for our problem, okay, and with the external force 4000 Newton, we get the peak stress as a 323 megapascal. Okay, so we will compare our FEA result with this peak value. Okay, so let's get started. Okay, so this is our previous example, okay, where we have more meshed with first order element TET elements, and we have seen the result. Okay, we get the peak stress as, okay, not this one, let me run it again. So the peak stress is 234 megapascal. Okay, so this is obviously it is a very coarse mesh. Okay, so let's refine the mesh near hole. So I will add additional mesh control, that is mesh refinement, and we'll select these edges. Let's keep 1 mm. Right click and create mesh. So now there is a little refinement near this hole. Okay. So this is the advantage with no PrePoMax. If you see, I have just updated a mesh and complete FEA model is updated. Okay, the material, solid section definition, boundary conditions, if you see, they are automatically updated because PrePoMax works on a geometry. Okay, it allows us to pick geometries so that when mesh is updated, the definitions will transfer to mesh automatically. Okay, so this is X symmetry, Y symmetry, and our pressure boundary, pressure loading condition. So the entire model is updated. I can simply go and create another analysis here. The TET C3D4 1 mm size near hole. Okay. Let's run this model and see the results. So now the peak stress we are getting is 283 megapascal, okay, from 234 to 283. But this is not even close to our analytical peak stress, that is 322 megapascal. Okay. So let's try to understand second order elements. We will let me save this model. Okay, this is the model of C3D4. Okay, so I will save it as a different model and set TET C3D10. So this is continuum 3-dimensional 10 noded element, that is second order TET elements. So this is a first order elements. I saved it as a C3D10 model. Let's make changes. So now we are running meshing with second order TET elements with the same mesh size. So I just need to change this basic mesh setting to advanced. Okay, so that it will open these options. Mesh type, I will say second order mesh, yes. And of course we will need to say mid-side nodes projected on geometry, yes. Okay, we are not interested in hex elements now, so quad dominated mesh, no. So I will create the mesh now. Okay, so this is the 1 mm size, but if you see there is a mid-side node projected on the geometry. So let me rename this model analysis. I will say C3D10 1 mm. Let me delete this and run this model. Let's see the results with second order 10 elements. So now we are getting peak stress as 313 megapascal. Okay. So let's note down, okay, the results. C3D4 with 1 mm size mesh refinement. The peak stress is 283 megapascal. C3D10 1 mm mesh refinement 313. So I can see second order TET elements give more closer results to peak stress. Okay, that is 323 with the same mesh size. Now we can say that C3D10, C3D4 has only two nodes, okay, in one element, whereas C3D10 has three nodes, one on mid side, so it captures. Uh, I mean, there are more nodes in a given geometry. So this is our C3D4, which has only corner nodes. This has mid side nodes as well. So one element has three nodes, whereas here the one element has two nodes. So this 1 mm size, the effective element size here becomes 0.5 mm. Characteristic length. Okay, so this is a 0.5 mm. So we are comparing 1 mm with 0.5 mm. So let's do one thing. Let's compare C3D4 with the 0.5 mm mesh refinement and see the results. So this is C3D10 model. I will open C3D4 model again. Okay, and I will just change the mesh refinement from 1 mm to 0.5 mm. So how easy it is? Okay, you just need to change the mesh and update FE model. Then simply create analysis and submit. So I will set that C3D4 with 0.5 mm mesh refinement. Run. Let's see the stress, peak stress. Okay, now it is 296 megapascal. So C3D4 is giving me 296. Okay. So we can see that even 0.5 mm and is not giving me no closer results when we compare with 1 mm size of second order elements. Okay, so second order elements are more accurate in stress concentration zones. So here actually we can get no, for both the elements we can get 323 megapascals, but here we are not doing mesh conversion study. We will see that in coming chapters. The purpose of this workshop is to understand the first order versus second order elements. So we are you know uh, of similar same mesh size, we are comparing first order and second order elements, and we can conclude. Let's write the observations. So first order elements are performing relatively poor in stress concentration zones, right? And that is the reason we should avoid the first order elements, basically first order TET elements in critical zones. Okay, so we can use first order TET elements as a filler elements, okay, but not in a critical zones or stress concentration areas. So even with the filler elements, we have to be cautious while using first order TET elements, because it may happen that no the elements, basically we have seen that no, linear tria element in previous section. They are also called constant strain triangle element. Okay, so this concept is also applicable to this 3D equivalent element, that is first order TET element. This is also constant strain TET element. So these elements are stiffer compared to second order TET elements, because it has only one integration point. So to capture the stress gradients, we need a very fine mesh no, compared to second order TET elements. So generally, we try to avoid these elements in critical zones, and in filler as a filler elements, we have to be little careful. For example, if we have two components, let's say this is a component one, okay, and this is a component two. Okay. Now we are applying displacement or force here on this component 2. Uh, no, since we might think, okay, this component, uh, no, this area is not so of interest, so we are modeling or meshing this zone with the C3D4 element. Okay. Now it may happen that when we apply the force, in reality, the component 1 and 2 are supposed to make contact with 10 Newton, but since C3D4 elements are stiffer, they might make contact with 12 or 15 Newton. In this case, though there are no stress gradients or stress concentration zones in component 2, but due to C3D4 elements, uh, and due to large displacement and bending dominated behavior of C3D4 or component 2, uh, the overall behavior, global behavior of the model is changing. Okay. So the takeaway is that use C3D4 elements as a filler elements, but with a caution. And coming to second order elements, okay, we already have seen that these elements are recommended for stress concentration zones. So If we are using TET elements, always prefer to use second order TET elements. And reason for that is, as we know, the second order elements, okay, they capture the geometry, curved geometry, and also the displacement variation is also quadratic. So first order elements, it's the linear variation of displacement, and constant strain, whereas second order TET element, it is a quadratic displacement variation. So these elements give enhanced results in stress concentration zones.